objects, so I think that it's really not necessary to make very long introduction. But I wanted to add some words because nobody spoke about accretion disk around strange stars, so I'm the first one, and according to me nobody calculated this before. And this is not interested only because this is about strange stars. This is also interesting because I think that we started to understand something really very basic concerning epicyclic frequencies around compact objects. So I would like to present some of our results, which I have recently obtained in collaboration with Wodek Kluźniak, with Nick Stergulas, and with Mateusz Wiśniewicz. And since I have now much more shorter talk that it was foreseen, if somebody of you is staying a little bit longer, there is a conference starting from Monday, in which conference students are allowed to present some results, and Mateusz Wiśniewicz will just present all our results concerning rotating neutron stars and strange stars and epicyclic frequencies. So this is the introduction. Everybody knows this picture, that there is one of the most important results of X-ray satellites, quasi-periodic oscillation. You know that there are a lot of models trying to describe what is happening near the compact object, and it is not necessary to make a review of these models because there are plenty of them, and already during the plenary session it was a lot of talk on that subject. I just only want to tell you that some of models just try to explain quasi-periodic oscillations using three important frequencies. The first one, there is orbital frequency. The second one, there is just radial epicyclic frequency. And the third one, it is vertical epicyclic frequency. Why we're just calling this like that, epicyclic frequency? Simply when you have a movement inside a disk, you can always just describe the movement just using one frequency in the radial plane and the other in the vertical plane. And here we have an expert, let's say, about one of the model, Louis Stella, so you can always criticize me. He is mainly in his model using orbital frequency to describe this quasi-periodic oscillation and the difference between orbital frequency and radial frequency. In my case, I will mainly concentrate on vertical epicyclic frequency. And already during the plenary talk, I don't know if all of you were during the talk of Wodek Kluźniak, he was just mentioned several modes of oscillation in disk. Mainly, it is very important to tell about line steering precession, which is, you know, the frequency is proportional to the difference between orbital and vertical frequency. So it is just telling us about modulation, what is the precession of the disk when you just take into account. So here we have a quite known figure. This is what is going with the frequencies. Just when we consider a black hole, the first figure, it is just non-rotating black hole. Here we have moderately rotating black hole, and here just rapidly rotating black hole. What you can see, maybe you cannot see because it's quite small figure, but here you see this upper line. There are just vertical epicyclic frequency, which is identical with the orbital frequency. This is a square of this frequency. And here you can see radial epicyclic frequency. And after that you have moderately rotating black hole, and here rapidly rotating black hole. And there is what I wanted to mention, just such kind of short summary. When you consider compact, let's say, when you consider a body in Newtonian gravity, non-rotating, all this frequency, I mean orbital frequency, radial frequency, and vertical frequency, they are just equal to each other. You don't have precession for non-rotating star. But when you just try to consider relativistic effects, what is going on? And here you can see on the first figure. just those frequencies, they are not anymore equal to each other. You can see the radial frequency is going down, is below the orbital and vertical frequency, and there is just a relativistic effect. But when you just would like to see what is the effect of rotation, what rotation is causing, there is something like that, that vertical epicyclic frequency and orbital one are not anymore equal to each other, and when you are going to higher and higher velocity of a star, you can see that the difference between this velocity are bigger and bigger. There is also the other effect concerning radial epicyclic frequency, that when you are going to higher and higher frequency, you can see that you have a higher maximum of radial epicyclic frequency, and at the same time the orbit is closer to rotating black hole. So this is just a short introduction. And how situation look like in the case of rotating neutron star. So we can foresee that in the case of the neutron star, we should have something similar like in a black hole situation, when we must take into account relativistic effects, and we should see that vertical frequency and orbital one not differs much more from each other. And here there is just epicyclic frequencies for neutron stars. Here you see orbital frequency. Here you can see the radial epicyclic frequency, and this is multiplied by 10 vertical epicyclic frequency. So it is multiplied by 10 because the difference between one and other is so small that there is almost identical, like in the case of moderately rotating black hole. So we see that for neutron star, just this line steering frequency is very small. How it looks in the case of strange stars. So I have no time to say about all models. I decided just to show you the model of two neutron stars, not neutron stars, I'm sorry, strange stars. I'm describing strange star by MIT Beck model, so everybody who is just doing the equation of state will try to kill me, but it doesn't matter, really. It doesn't matter what kind of equation of state of strange star I'm using. The most important thing that we have a model different from neutron star, that we have self-bound matter, so we have high density jump at the surface, and just to see what are the difference between neutron stars and strange stars. So what we can see here, there are just the solutions using a fully relativistic code RNS, which was just developed by Mixter Gulas and collaborators. We just modify this code to be able to study strange stars and also to study this epicyclic frequency. And what is going on? Maybe it is not good visible, but let me explain what is here. Here you have frequency, here you have the distance from the compact object, there is R divided by mass of the star, and the radial, the dot lines correspond to radial epicyclic frequencies, the dashed lines correspond to vertical epicyclic frequencies, and just solid lines correspond to orbital frequency. And the red lines are for more rapidly rotating star. In this case, there is around 1 kilohertz, while the black one corresponds in this case to 600 hertz rotating star. And what you can see, the first effect when you look at a radial epicyclic frequency is a different effect than in the case of rotating Kerr black hole. I mean that if you are going to higher and higher frequency, the marginally stable orbit is pushed far away from the surface of the star. So this is different than in the case of rotating Kerr black hole. And what is going on with vertical epicyclic frequency? This is something completely different. I mean, there is completely new effect. For the first time, you can see that vertical epicyclic frequency is higher than orbital frequency. it is different behavings than in the case of rotating black hole. In the case of rotating black hole, the vertical frequency, for the general relativistic effect, was pushing down, was smaller and smaller, was decreasing. Here it is increasing. What is going on? And in fact, this difference is quite huge, so we suppose that we should have significant modulation at the inner part of an accretion disk, having such kind of difference between these two frequencies. The same situation is when we are taking a star with higher mass. So before I will go to explain this thing, some of you just already know the answer because Wojtek said what is the answer, so this is not a mystery for some of you. But I wanted to show you how it is looking like when we are just taking into account a star with 1.4 solar masses, what was on the left side on the previous transparency, and what is going on when we are just going to far and far away from the compact star, rotating star. You see that if you are far away from the compact object, rotating strong star in this case, or if you are just going to higher and higher masses, no, this is for the same mass, so it doesn't matter. For smaller frequencies, you see that situation is because this is the difference between vertical epicyclic frequency and orbital one. So it seems that for those curves, the situation looks similar like for moderately rotating neutron star and for moderately rotating black holes. I mean that you have vertical frequency smaller than orbital one, but close to the rotating object, close to the strange star, you have different situation. You see that there is a change of sign and that the vertical frequency is higher, and the more high frequency of rotation, the higher region and the bigger difference between these two frequencies. So what is the reason for such kind of behavings? It seems that there is contradiction to relativistic effects. It is completely going to different direction that we're supposed to be. And the answer comes from Newtonian theory. So when you look, we recently found analytical formula for Maclaurin spheroids, the purely Newtonian calculation. We found here you have the frequencies versus the distance from the star. And what you can see, the first thing is that such kind of relation holds, that the square of the vertical frequency plus the square of radial frequency is 2 times orbital frequency. And you see how it is looking like. You have radial epicyclic frequency here, you have vertical frequency here and orbital here, and somebody of you should really notice that there is something strange happening here. You see that radial epicyclic frequency is going to 0 in Newtonian theory. In Newtonian theory, so marginally stable orbit, it is not something like that which exists only in general relativity. There is something like that in Maclaurin spheroids, in rotating Newtonian body, you have also marginally stable orbit. And why it is like that? This is the effect of oblateness. Simply when you have a rapidly rotating object, the metric is changing, and thanks to the oblateness, you can have marginally stable orbit, even in Newtonian theory. The analytical formula were published in 2002 for marginally stable orbit in our paper, but it was also noticed by Leszek Dumik and Eric Bourboulon at the same time that marginally stable orbit exists in Newtonian theory. And you see that this is just the effect of oblateness, that you have always vertical epicyclic frequency higher than orbital one. So what we have done, just using fully relativistic code, RNS, we just, it is possible to do this for strange stars. So this is why I said that we decided to consider strange stars, because you cannot just make Newtonian neutron stars, because they have minimum mass. And in the case of strange stars, you can consider very small objects. And in our case, we just took a strange star described by MIT Beck model, standard one, with very small masses, 10 to minus 3 solar masses. And what you can see here, solid lines correspond to analytical formula derived by us for epicyclic frequencies. And these dots, they are just numerical one for such kind of small strange stars. So you can see that the agreement is really perfect. Here, it is just for one frequency of rotation of strange star, and here for you just to see that we were also considering all possible frequencies for rotating strange stars, so starting from non-rotating star, going to a very rapidly rotating star. You see that agreement is really perfect when you look at analytical formula and strange one. So, I don't have so much time, so only I wanted to mention here that we can ask, is it something, artificial, just only existing for strange star, that we can see that we have the effect that, that vertical frequency is higher than orbital one, and for some frequency much more higher than orbital one. So we should suppose that we can have very strong modulation, or something like that also can be seen for a neutron star. And here I just only give you example. I'm cheating a little bit in the sense that, of course, I'm not showing you only results for neutron star, but only for rapidly rotating neutron star described by one of the known equation of state, FPS equation of state. And they are just neutron star rotating with maximum frequency at mass shed limit. And here you can see how looks the dependence of this frequency versus mass of the star for this rotating very fastly neutron star. And you can see that, that for small masses, I mean smaller than 1.5, also for neutron star, the vertical epicyclic frequency is higher than orbital one. So such kind of effect exists and can be seen also for neutron star. But of course, for much more massive, when really relativistic effects are very important. I mean, what I wanted to mention here, that we can see always two effects fighting with each other. The relativistic effect, which is just trying to make this vertical frequency lower than orbital one, and also making the increase of the value of vertical epicyclic frequency. And the other one, which is purely Newtonian effect and caused by oblateness of the star, rapidly rotating star. So I'm going already to conclusion. That in my talk I just showed that for strange stars that we are just observing two different effects. One is connected with relativistic effect and the other with oblateness. And in the case of rapidly rotating star, it is quite promising effect because we can see quite high modulation in the nodal precession. And also it can be observed in rapidly rotating neutron star, but it's necessary just to check this for the other equation of state, for the other frequencies of rotation, not only maximum one. And Mateusz Wiśniewicz is supposed to present results for FPS and for different models of strange stars. So thank you very much.